Okay, next we go to the schematics or the arrangement of DC shunt generator. So same like DC shunt motor, we have here field branch. We have here armature. So now we put a force of the shaft is turning the motor. So the motor will generate EA. So EA will be higher compared to VT. So the current will flow through IA back to VT. So we have here EA is equal to VT IARA plus VT. Okay. So you draw or use fabricate the circuit and you are able to derive the equation. So IF is still the same, VT over RF. So when we plot the output behavior of this generator, so no more we plotting in terms of speed like motor. So we generate terminal voltage. So VT versus load. The more load you put in, so the lower the VT will drop. So drop due to resistor of here and the resistance of RA here, and also drop due to field mechanic effect. So the higher the current or the load you put in, and the lower the voltage, generated voltage at the terminal will drop too. So then the DC series generator, same like DC series motor. So the flow of your IA is back from EA to VT. So all the current is the same. I load, I armature, I series is the same. And the equation also, you just change into minus. Okay. In terms of your generated voltage at the terminal, not the same like DC shunt generator, because at the minimum load we already have voltage here, very high starting voltage. But load for DC connected generator, it will be linear, and from zero load the voltage will increase. But when the load increase also, the voltage will be higher. And the higher the load or the higher the speed, and the higher the generated voltage. But after certain amount, due to series drop and armature resistance drop, so we have a lower terminal voltage. So we combine between the advantage of series and shunt, so we have this kind of commutative compound generator. So we have commutative compound. So the dots means the entrance of your current, and so you arrange the arrangement back to back or side by side of this field current field arrangement. You have a commutative compound generator. Okay. So from the circuit, you're able to derive the equation. So this is the net flux of your circuit. Means that the arrangement of your circuit here will mean how much the flux, net flux of your circuit. We understand that further in our example question later. Okay, in terms of terminal voltage, if we have an overcompound, and this is the shunt type, so the drop is quite obvious. So if we put in arrangement of undercompound, so it improve a little bit. If a flat compound, so it will improve a bit. If overcompound, it will further in terms of range or the response, maybe not so good lah. It will be increased, and the higher the load you put in, the higher the voltage generated. So the best is your flat compound, flat and also under compound. Over compound means that the what is the meaning of the over compound? Flat compound and under compound. So try to find out your term of this statement. Okay, then we shall go to the machine losses. So efficiency means that the machine will not drop in terms of the performance when we put load into the system. Okay, from that we should indicate, or we should recognize what are the contribution of the losses, and which lessen the efficiency of the machine. So we have a few so-called obvious, or the losses that should put into account in our calculation or determination of this machine, either for generator or motor. Some of it are copper losses, brush drop losses for DC. We don't have a brush on other kind of motor, but this is focused on DC. So brush drop, mechanical losses, and friction on the so-called bearing, on the gap of your between rotor and motor, stator, and the core losses, and the losses inside your magnetic elements, and the stray losses, and the thickness of your lamination, steel lamination. Yeah. So where the copper loss comes from is occur in the armature and also the field winding of the machine, and in the stator and also in the rotor. And so armature loss considered as, or calculated from the how much the armature current goes into your circuit of at that time times the your armature resistance. So this will change accordingly. This one will be fixed. So armature losses will be will increase or decrease based on the load and condition. And we have field losses. Field loss, the higher the RF, the higher IF, so we have higher PF. And we have copper losses and armature losses. So both of these armature and field losses we consider as copper loss. So you can calculate both separate as armature and field, or you can combine together to become a copper loss element. Then we have a brush drop loss and power loss due to contact of the brush of the machine. And we use carbon, so we have resistance. You cannot use copper, and because carbon will deplete accordingly, will not damage the structure of your rotor, but other than that element, maybe cannot use now. So we have a PBD, which is drop loss due to the voltage drop across your brush. So P equal to VI. So V of the drop times the armature current that transfer from the circuit into your rotor, or from your rotor from generator into your armature. Then we have the core loss, which are the hysteresis loss and eddy current loss occurring in the metal of the motor. And so that's why we have a elimination of construction for the motor and the stator, such that we are able, or we should reduce this eddy current loss. So we can measure only, we cannot calculate this eddy current loss. Then we have a mechanical loss of a system, which comes from the friction and windage. And friction loss are the cause of friction of the bearings and of the machine. And the better the bearings lubricant we put in, so the lower the friction loss will occur. Windage are caused by the friction of between the moving part and the air inside the motor casing. So we have motor inside your encapsulate casing. So the more the gap, so the lower the losses. The higher the smaller the gap, the higher the losses. But if you increase the gap, so the flux linkage will be lesser. So that's the pro and cons. You reduce the gap, so the linkage will be better. But in terms of losses, it will increase. We have another one, which is stray loss, which consider this one as a losses that cannot be placed on the other kind of losses, previous category. So we take as 1% of the full load condition. P in how much? So 1% of it considered as stray loss. So in terms of summary, or in terms of figure or diagram, so this is the input power for generator. How much we put in, the gap or the range is very high, but at the end the output power will be much lesser due to losses due to IR, core loss, mechanical loss, and stray losses. So this is the way or the point of the shaft that we measure in terms of their torque and the conversion energy lah. So this is generator. For motor, how much power we put in terms of electrical, how much output turning force at the shaft. So the losses due to electrical is on the copper loss. This core loss, mechanical loss, stray loss is the losses measured after the conversion. So this is for the motor, this is for generator. Okay, in terms of equation, P conversion is equal to P in minus all the losses involved inside the generator. Electrical power output is of the machine for the, this is the motor, mechanical power output. So this is the generator, the electrical power output, and the P conversion minus all the internal losses. For that one for generator, this one for motor. Conversion power is equal to P in minus all the losses here. Mechanical power is equal to P conversion minus all the internal losses. So in terms of efficiency, of the DC machine defined by mu equal to P out divided by P in times 100, or P out minus the losses divided by P in. Usually we use P out divided by P in. So you continue with this question. For example, on 9 horsepower, 220 volt of terminal voltage. This is for generator. This is expected output. So full load. So this is rotation, rated rotation. All the elements given. So what you have to do is that you transfer all the data into circuit. Then find out what is the field current. Then generator efficiency at full load if input power is 36k. Okay, 36 kilowatt. So that's all for part 2, DC motor and generator in terms of their characteristic, behavior, and so on. Okay, later we'll go into your next motor. So for this motor, I will provide the tutorials, question, and we'll discuss the answer on the session that will be decided later. Okay, thank you for your attention. Good luck and have a better study, inshallah. So you'll understand DC motor or DC machine good in a good manner. Thank you very much. Assalamualaikum.